Hi, welcome to case study of simple linear regression. Here, the simple linear regression in the sense we will have only single variable x1, that is also called univariate linear regression. Here, x and y values are given in the table. This is the data set for considering linear regression case study. Here the given equation is y equal to mx plus c, and the given data set is displayed in the given plot. For example, 1 comma 3, so this is the data point 1, so 1 comma 3, and this is 2 comma 4, and this data point is here 5 comma 5 approximately we have mentioned in the plot, and this is 4 comma 4, and this one is 3 comma 2. Based upon that, we will calculate the slope for given data point. The slope equation is here summation of x minus x mean, this is the mean, into y minus mean y, and summation of x minus x mean whole square. Here, when you are applying the calculation, you will get the mean x is 3, then here mean y is 3.6. So we have calculated the mean y and mean x 3 comma 3.6. So for mean 3, so you will get the vertical line, and then mean y you will get the, this is the 3.6, we are getting the horizontal line. So this is the data point, we are calculating the mean x comma y, mean x comma y, we are calculating the data point. Then we have to apply the linear equation for calculating slope m and constant c, that is using for slope, I mean y intercept. So when you are applying this equation, already we have calculated the mean x and mean y, then we will apply to calculate the x minus x mean. Okay, so x minus mean x we have calculated here, and y minus y mean we have calculated here. So these are the values given, and x minus mean x whole square we are calculating. So x minus mean x whole square is here we are taking the summation of x minus x mean x whole square, so that is the 10. Then we are applying the x minus mean x and x minus mean y. So these are the values we have calculated by using this multiplication of these two terms. Then summation of that value is 4. So here this summation has to become here summation of x minus mean x into y minus mean y divided by x mean summation of x minus mean x whole square. So x minus mean x whole square is the 10, and multiplication of two terminology, x minus mean x and y minus mean y is 4. So this is the slope we got 0.4. So 0.4 is the slope here. Then here x is we have calculated here the mean x, this is the mean x, right? And mean y also we have calculated this data point. So this is the data point mean x comma mean y. Then we can calculate the c when you are substituting the values here for all the variables, then you can calculate the c. So y intercept is here approximately to 2.4, this line. So this is the line we are getting the 2.4. After that we will plot the data points in the graph by using the Python. So you look at that here, these are the actual data point, and for this data point this is the predicted value. So predicted value we have calculated here by substituting the m value and c value, so y intercept c value. This is the equation is y equal to mx plus c. When you are substituting the values, you are getting, this is the data point 1 2.8, data point 2 3.2, data point 3 3.6, data point 4 4.0, data point 5 4.5. 4. So this is the value, predicted value we got for the all 5 data points. So here x value is here. So this x value is 1, 2, 3, 4, 5. So this can be indicated by 1 comma 2.8. So that is the 1 comma 2.8 here, this data point. So this is the 1 comma 2.8, and this one is 2 comma 3.2. So 2 comma 3.2 is this one. So this one is the 2 comma 3.2, and next one is 3 comma 3.6. So 3 comma the x is the 3, so this value 3.6 is this one. So 3 comma 3.6. This one is 4 comma 4. So 4 comma 4 is predicted value, same data point here, 4 comma 4, and this one is 5 comma 4.4. So 5 comma 4.4 is this one. So 5 comma 4.4. So now we have predicted the values for all 5 data samples, and actual data is already given. So based upon that, we have to calculate the error for all the data points. So by applying the mean squared error method here, this is mean squared mean we are taking number of samples we are taking, mean squared error method. So here we are applying that difference between the actual output minus predicted output. So based upon that, we can apply the mean squared error, which will minimize the error in the linear regression to find out the best fit line, right? So best fit line will find out here. So based upon that, decision boundary will be drawn here, based upon predicted values. Here in the MATLAB, we have applied the data points, some of the data points right here in the iteration 0. So here, to minimize the error, we can update the theta values. We can update the theta values in the equation y equal to theta 0 plus theta 1 x1. Here x cannot be changed, so theta and theta 0 and theta 1 can be updated by using the formula, that is the gradient descent formula. So here we can start from the iteration number 0 to, you can apply maximum number of iterations, 50 or 100. So any number of iterations you can apply here, and initially slope is also 0. So when your y-intercept is 0 and slope is 0, here this is the data points. All data points are converged on the single position. So 0 comma 0, 0 comma 0. So here the slope is 0, and here the y-intercept is also 0. So that's why it is converging on the same data point, right? So the iteration 0, m is 0, b is 0. Then we are starting with some number of iterations. Then linearly you look at the data points are arranged. Still we are our slope is 0 here, slope is 0 here. Now we are updating the iteration number 1. Here slope is 0.404, and that y-intercept is 0. So y-intercept is 0, and slope is here close to the 0, 0.04. So that's why the data point is here. Then we are increasing the iteration number 20. Here the points. So here the points also arranged in the plot. In the iteration number 1, the data points are arranged in this manner, the predicted values. And now in the 0.01 is the y-intercept, m is the slope 0.59. So this is the 0.59, this is 0.01. So this is the place we got the center point for the decision boundary at the iteration number 20. Then for at this position, decision boundary is appearing in this pattern. Okay, decision boundary is appearing in this pattern. So data samples are appearing here, the decision boundary is appearing in this pattern. Now the m value, that is the theta 1 is also this one, theta 0 is 0.01. Then iteration number 47, slope is updated 1.03, the y-intercept is 0.02, so slope is here 1.03. So this is the position. C is, I mean, y-intercept is 0.02. It is close to this position. Then at that time, the data points are here, and the decision boundary is, look at that, close to the data points. So previously, the decision boundary was here in this position, right? Then now it is moving towards this direction, anti-clockwise, right? Then in the iteration number 99, slope is 1.36. So this is the 1.36 slope, and 0.03 is the y-intercept. So for these values, you look at that, our decision boundary is almost best fit to the given n number of data points. So like this, when you are applying the different iterations, okay, iteration numbers, right? When you are increasing the iterations, slope, I mean, slope is the theta 1, b is the theta 0. So theta 0 and theta 1 is updated until getting the best fit of decision boundary. So until that, we can do that linear regression process. Thanks for watching.